Let's continue our study on tensors by focusing on three important types of tensors which arise in dynamics. The first one of them is the symmetric tensor. As you can guess, a symmetric tensor is a tensor in which the transpose equals to itself. Okay, so for example, if the matrix of S in some coordinate system is then these two are equal, these two are equal, these two are equal, so it's a symmetric tensor. So no big deal about it. So a symmetric tensor will arise very frequently in dynamics in the form of the so-called inertia tensor. You are currently used to inertia being a scalar, and that information is wrong. Inertia is actually a tensor, and it will be an important fulcrum in everything that you do in dynamics. And the inertia tensor is symmetric. Okay, so that's the importance of the symmetric tensor. So what are the specific properties of a symmetric tensor? If S is symmetric, which and has principal values Si, then we are ensured that the Si are always real. It is possible that S1 equal to S2 equal to S3. So for example, the unit tensor will always have the look 1 1 1 0 0 0 0 0. It is obviously symmetric. However, the eigenvalues are lambda 1 equal to lambda 2 equal to lambda 3 equal to 1. So while I am saying that they are real, they can all be the same. Some of them can be different, all of them could be different. Notwithstanding the fact that whether the principal values are same or different, you are assured that there will be three principal vectors Ei. Moreover, these principal vectors will always be orthogonal. Okay, fantastic. Because they are orthogonal, I can always put them together to make up a coordinate system, and this coordinate system is given a name. It's called the principal coordinate system. Okay, the principal coordinate system of the symmetric tensor. Okay, and inside this principal coordinate system, as we have discussed in the previous example, the matrix of the tensor will take a particularly simple form, a diagonal form, and you can represent it as this, and in tensorial notation you can write it like that. So the summary of this slide is that a symmetric tensor is always diagonalizable, and this action of a symmetric tensor therefore is simply a stretch along its principal vectors. Okay, there is another type of more specific symmetric tensor in which if the principal values of the symmetric tensor are always positive, then it's called a positive definite symmetric tensor. So what will turn out is that the inertia tensor is actually a positive definite tensor, because what will turn out is that all the principal inertias are always greater than 0. Okay, so in this course the particular tensor which will arise is that of the inertia tensor, which will be a positive definite tensor. Okay, so now what I will do is I will quickly give you an example which will demonstrate this important property of a symmetric tensor, that its eigenvalues are always, its principal values are always real, and no matter what they are, whether they are the same or different, we can always find three principal vectors which are orthonormal. Okay, all right, so let's do the example. So the example I had in mind was this tensor A, which in some coordinate system, let's call this coordinate system E, has components given by 3, 2, 4, 2, 0, 2, 4, 2, 3. You can do your linear algebra and you can find that the principal values, lambda 1 is -1 and it is the same as lambda 2, while lambda 3 is different, it is equal to 8. So right now I have one repeated principal value. Okay, so now we should be worried. If we have a repeated principal value, are we assured that we will still be able to find three different principal vectors? Yes, because A is symmetric. So because A is symmetric, we are guaranteed that there will be three principal vectors which will be orthogonal. Let's go about finding them. To begin with, corresponding to lambda 3 equal to 8, you can easily find that V3 in this coordinate system E will be 1/3 2 1 2. Okay, so we can draw this if you wish. Let's kind of draw this. So let's say 2 2 1 2. So basically let's see, I got this, got that, got this point, has to come out by 1. So this is V3. Okay, let's give it a different color this time. Give it this color, this. Okay, very good. Okay, so here's my eigenvector, or rather my principal vector V3. Now what this property tells me is that the other two principal vectors, they will exist and they will be normal to V3. That means I expect them to lie in a plane normal to V3. Okay, so what I expect is that expect V1 and V2 to lie in plane normal to V3. Okay, so let's check whether that is indeed the case or not, and if it is, what are these two vectors V1 and V2. Okay, so what we do is that let's go back and do the usual computation to find V1 and V2. To do that, we have to look at A minus lambda 1 into 1. We have to solve this equation, right? Right, that's how you solve for the principal vectors. When you do this, you will get this matrix equation: 4 2 4 2 1 2 4 2 4 times the components of this V, V1, V2, V3. Okay, and this should be equal to 0. Clearly all these rows are the same. That means that the principal vector corresponding to lambda 1 and lambda 2 must satisfy this equation, right? So what we are saying is that the principal vectors corresponding to lambda 1 and lambda 2 must satisfy this, right? But really, what is this equation saying? This equation can be written as V dotted with V3 equal to 0, because remember, what was V3? V3 was, well, here it is, V3 was 2 1 2 2 1 2, right? That's 1, right? So Okay, so that means that the principal vectors corresponding to lambda n1 and lambda 2 are normal to V3, which is what we were saying over here, and which is what this statement is saying, that the principal vectors are orthogonal. There is still no guarantee that both V1 and V2 will exist. One of them will exist and one of them will lie in this plane, but why should there be two of them? Well, that is clear. It's clear because all we need to do is find two vectors which are normal to each other and which lie in this plane, which is normal to V3. We can find infinity, okay, an infinite number of such vectors. So let's write that out. So we can now find any pair of orthonormal V1 and V2 in plane normal to V3. So for example, it could be V1 equal to 1 by root 5, 1 minus 2 and 0, and V2 could correspondingly be 1 by root 45, 4, 2 minus 5. V1, you can check V1, V2, V3 are orthonormal principal vectors of A, and they satisfy these properties. So you have seen something very interesting. You began with a symmetric tensor, bad choice. You began with a symmetric tensor. It had one repeated value, principal value, but you did not worry. You were able to find a set of 3 orthonormal principal vectors of A. And this orthonormal principal vectors of A can now define the principal coordinate system of A. Okay, and this principal coordinate system of A can then be used for diagonalizing this tensor. Okay, all right.